Alright, today we're on Unit 6, Subunit 7, which is called vapor pressure. Vapor pressure is simply the pressure that's exerted by a vapor that is located above a liquid or a solid at a given temperature. So let me draw a picture so that I can explain what it is that we're talking about when we're talking about vapor pressure. I'm going to use this screen right here to draw it. Let's say we have a closed system. Now, a closed system means that you have a sealed container, and in that sealed container, you have a liquid. We're going to make it a liquid. It could be just as easily be a solid, but we're going to make it a liquid. And I'm going to draw a particle diagram of that liquid. Now, these molecules, whatever these molecules happen to be, we're going to make them water for now. Okay, this is liquid water, have an attractive force towards the other molecules. So there's forces of attraction that are in between these molecules. We call them intermolecular forces of attraction. And they're holding on to each other. But this top layer of water molecules that's right up here by my cursor, they want to escape. So when they escape, okay, they're going to go into this area that's above the water. Oops, I made my circles a little bit big. All right. And we're going to form a water vapor that's up here in this space. And that water vapor is bouncing all around in this space and hitting each other and hitting the walls of the container. They're also hitting the surface of the water that's down here. And all of these crazy arrows that I drew are what we call vapor pressure. They're the pressure that the water vapor is exerting on the inside of this container. If a molecule, in this case water, or any other molecule, really wants to evaporate, its vapor pressure is going to be high because it's going to have lots and lots of molecules up here in this space above the liquid. So if we have a molecule that has a high vapor pressure, it has to have wanted to evaporate very badly. And there's a couple of different things that allow molecules to evaporate very quickly. They can evaporate very easily if they have low, or I should even say weak, not low. Low's not a really good word. Let's change that to weak. Weak intermolecular forces of attraction. And that means they're not really holding on to each other very tightly. Now, some molecules hold on tighter than others. Water is a pretty tight molecule. It's hugging other water molecules very tightly because it has something called hydrogen bonds. However, there are other molecules that hold on very weakly. So the weaker your intermolecular force of attraction, the higher your vapor pressure is going to be, because you're going to be able to escape into this space and you're going to be bouncing off the walls of the container more than if you stayed in the liquid phase. The other way that you can exert a high vapor pressure is to be a small molecule, because small molecules tend to evaporate quicker than larger molecules. So small molecules also have higher vapor pressures. And the last thing, which is going to be the one that we're going to focus on in the next slide, is high temperatures. High temperatures give the molecules enough kinetic energy to overcome the forces of attraction that are holding them together. So remember, kinetic energy and temperature are the same thing. So if you have high kinetic energy, you're going to have high vapor pressure because you're going to escape into this space more easily. You're going to have enough energy to become a gas vapor. Okay, so what I did was I flipped to this table, which is table H on our reference tables. Table H. And table H gives us the vapor pressure of 4 different liquids: propanone, ethanol, water, and ethanoic acid. And what they do is they actually give us the vapor pressure for each one of these liquids at a specific temperature. And down here, I cut it off a little bit. I don't know if you can see it on the recording, but down here is temperature. in degrees Celsius. And what they'll ask you to do is they'll ask you which one of the following has the highest vapor pressure at a specific temperature or the lowest vapor pressure at a specific temperature. So let's take 75 degrees right here, 75 degrees Celsius. And if you look at 75 degrees and you follow it up, you'll see that ethanoic acid basically has a vapor pressure, okay, of 20 kilopascals. That's a unit for pressure, 20 kilopascals at 75 degrees. If you go up to water, water has a vapor pressure of 40 kilopascals. So it's a little bit higher vapor pressure. If you go all the way up here, let's see, am I on the right one? Yeah. Ethanol will have about 85 kilopascals. And then if we follow it all the way up to propanone, propanone has 150, 60, 70, 80, 180 kilopascals. So which one is going to evaporate the easiest? Propanone, because it has the highest vapor pressure. The more vapor pressure you have, the more molecules you have in that space above the water. The other thing that they will ask you is which one of these four substances has the strongest intermolecular forces of attraction? Well, keep in mind that if you have strong intermolecular forces of attraction, your vapor pressure is going to be low, okay, because you're holding onto the molecules very tightly. So, if you have strong intermolecular forces of attraction and low vapor pressure, here's my vapor pressure, that's my lowest, 20. Right? So this guy, ethanoic acid, is going to have the strongest intermolecular forces of attraction. And propanone is going to have the weakest intermolecular forces of attraction. Okay? So strong intermolecular forces of attraction, low vapor pressure. Weakest intermolecular forces of attraction, highest vapor pressure. All right. All right, one last thing about vapor pressure is when the vapor pressure and the atmospheric pressure are equal to each other, we have a situation in which the boiling point is reached. Okay, and so I want to take a look at this again. Right here, 101.3 kilopascals is standard atmospheric pressure. Atmospheric pressure. That's the standard temperature and pressure that we always talk about. If you are at standard pressure, if your atmospheric pressure and your vapor pressure are the same, atmospheric pressure and vapor pressure are equal. If these two things are equal to each other, we are at the boiling point. So let's say our atmospheric pressure and vapor pressure are 101.3 kilopascals. If you follow that over, that's standard pressure, and you follow it over to water, which is right here, you'll notice that water boils at 100 degrees Celsius, which that's good news because that's what we know it boils at. If, however, we lower the pressure, let's say we lower the pressure to 50, so we're about half, a little bit more than half of the atmospheric pressure. Well, now the water is going to boil at 75, 87-ish, 87 degrees Celsius. So if we lower the pressure, lower the atmospheric pressure, we're going to boil at lower temperatures. Okay, and you can see that here. Here's standard pressure, followed across, you get 100 degrees Celsius. If we lower the pressure, the vapor pressure / atmospheric pressure, because when atmospheric pressure and vapor pressure are equal to each other, we boil. So if we lower it to about 50, now we're going to have to only get the temperature to about 80 7 degrees Celsius. Be careful down here because these guys go by 5s and these guys go by 10s. Sometimes that throws people off. So this is 75, 80. Oh, that should be 83, not 85. 75, 80, 85, 90, 95, 100. So this should be 83, not 87. Okay, so just be careful with that. Just wanted to point that out. Okay, so just keep in mind a couple of things here. If atmospheric pressure and vapor pressure are equal, you're at your boiling point. If you lower your atmospheric pressure, basically you lower your vapor pressure as well, because they're equal to each other, you're going to boil at lower temperatures. Okay? All right, all good.